Hello and welcome back to Galileo's Bench. My name is Greg Perugini, and as you no doubt noticed, this is a little bit different of a lab format. We're not in the laboratory where I'm talking to the whiteboard and doing the experiment with the kit on the table. We're doing this here. It's a little bit of close work as we work through Kepler's second law and do an ellipse. So this is probably a better format for us. So let's get through it. So we're going to talk about Kepler's laws. Kepler formulated these laws using the data that he got from Tycho Brahe, who gathered that data over many, many years. And he formulated these three laws that tell us how the universe really moves. Not only the movement of planets, but the movements of galaxies as well. Kepler's first law is kind of straightforward, that all planets move in an elliptical orbit with the sun at one focus. And that's different from what Copernicus had said, because what Copernicus had said was that these would be perfect circles. If we say the sun is at, and we have a pushpin in, and we have a distance here of 14 blocks, we'll get to what that means in a little bit. But we have the sun at one focal point for our ellipse. Kepler's second law says that as I go through an orbit, a line that connects the planet to the sun will sweep out equal areas. So if I'm going 1 month here, 1 month here, obviously I'm covering more distance in this 1 month than here. And on extremely elliptical orbits, you are moving much faster closer to the sun than when you are farther away. Now, Kepler's third law is a bit confusing. In fact, we have in here inserted some of Newton's work. But don't sweat the math, because we're going to do this lab based on the second law, and the math should be pretty straightforward. So what you're going to need: a pencil, a ruler, a calculator, a string looped to about 24 centimeters, give or take. Mine is 24 centimeters. In other words, the string is 24 centimeters, and that distance between my thumbs is 12 centimeters. You need 2 pins, just like I have set up here, and a little bit of patience. So let's take a closer look at what we're doing here. So I have the sun here, okay, at one focal point of an ellipse. Now, how we're going to build this ellipse is I'm going to put this string here around, and then I'm going to hold it tight, not pulling the pins out, and draw. Notice if I had just one point, it would be a perfect circle, but with the ellipse here, it is using 2 focal points. So, well, there you have it. Fairly straightforward, right? Not too difficult. And there's our sun right here. And this particular, let's say this is a comet that's going around. Let me take a point here. I'll call this point A. If I measure the distance here, it's 11.5 centimeters, or 11.5 blocks rather, which is, or 11.5 centimeters, excuse me, that's correct, and it is 23 blocks. Let's use this scale here. One block of movement is equal to 1,000,000 kilometers. Okay? So let's do this. If I move 1, 2, 3, roughly 3 blocks down to B, I can draw these lines. And I'll give you this calculation. It's pretty straightforward. And how do I get this? And this is roughly a triangle, pretty close to a triangle in approximation. And of course, the area of a triangle is 1/2 base times height. 1/2 the base, this part, 23 times 3. We went 3 spaces. Gives us that area, which is, if you do the math, let me get my calculator out. 1/2 times 3 times 23 gives us 34.5 blocks of area. We can even call it of sweep if we want to do it that way. This area here is 34.5 blocks. We traveled from A to B. Let's say that's 1 year. From A to B is 1 year. So I can get my speed pretty quickly because I did that 3 blocks, 3,000,000 kilometers in 1 year. So that's my speed. So now let's take a point here. We're going to call this point C. Okay. Now this distance here, that's 9 blocks. Where would D be? Is it here? Is it here? Is it here? That's what you're to calculate. You want the sweep out, the area that's swept out, to be the same, according to Keplers' second law, 34.5 blocks. Now you can count them there, do the math that we just did before. You're going to get an estimate naturally since this is a curve and it won't be a straight triangle, but you get the idea. And then you're going to get this distance here, which will be different than our 3,000,000 miles, 1,000,000 kilometers. But that distance from C to D, according to Kepler's law, is in the same amount of time. We're covering more distance in the same amount of time. The speed, in other words, the speed from A to B is slower, according to Kepler's law, than C to D. So I want you to try your hand at trying to figure out what this speed is. Calculate on your own what the speed to A to B is. It will depend, of course, on how large your distance here between the focal points are, and how large your loop in the string is. Right, doing this calculation here, and where you settle to make the number of blocks, the sweep out, the same. So that's the lab. Take your time and make sure you understand the second law. The amount of area here swept out is equal to the amount of area swept out here. And the implications here on the experiment in terms of the speed between A and B and the speed between C and D. And complete the lab material as per your instructor. And good luck.